Okay, this is going to be our fourth video in our current resistance and EMF module, and it's going to be our final video in this series. In this video, we're going to look at the sort of last topic from section 25.4, which we didn't cover in the last video, which is potential changes around a circuit. We'll take a look at that, and then we're going to look at the entirety of section 25.5, which is energy and power in electric circuits. And we're not going to look at 25.6, which is the theory of metallic conduction. We're not going to be doing that section in this course, so you guys can ignore that. So let's get into the content here. So to begin with, as I mentioned, we're looking at this topic from 25.4, which we didn't do in the last video. We're looking at potential changes around a circuit. Okay, so the net change in potential energy for a charge Q making a round trip around a closed circuit has to be zero, right? We can't have a change in its potential energy because it's coming back to the point that it was to begin with, right? This means that the net change in the potential around the circuit has to be zero, right? If there's no change in the potential energy, the potential must also be zero, right? And this means that the sum of the potential differences and the EMFs around the loop must also add up to be zero. And so we end up with this expression here. And what are we sort of looking at here? We can imagine that this is sort of, this would officially be our EMF, and this is the internal resistance of whatever the source is that's providing this EMF. So this would kind of like be the terms that the battery or whatever would be responsible for, and this IR would be the sort of potential difference across the rest of the circuit, right? This is like our Ohm's law, V equals IR. We just have the IR here. So we need it to be such that around the loop, this is a loop we're going to be looking at in a second here, so that around this loop, when we say start from over here, and we go around the loop and we come back, we're going to have no net change in potential difference. Okay. And so let's take a look at sort of what the plot of this might look like. So if we set the negative terminal of our source to be a zero potential, we can kind of see what this is going to look like, right? So we're going to have zero potential at the negative terminal of our source. As we go through our source, we climb all the way uphill. Something is pushing these charges up this potential hill, is a way to sort of think about it. In the case of a battery, this would be the force supplied by not the electric field, right? This is what we would have called F sub n when we looked at this previously. So we have this increase in potential while we're moving across the conductor inside the battery. Before we get to the internal resistance of the battery, we have a constant potential. Then as we go across the internal resistance of the battery, we have a potential drop. Now we're outside of the battery. We're traveling down our conductor again, so no change here. All these points along this conductor are at the same potential, and then we hit the external resistance, right? We hit this external resistor, and our potential drops all the way down to zero, and stays zero all the way around the loop until we come back to the negative plate of our source of our EMF, right? And so that is what the potential changes around a circuit would look like. Okay. So now we want to sort of change gears slightly, although that last topic related pretty well to sort of thinking about what's going to be happening in this section. We want to now talk about energy and power in electric circuits and circuit elements. And this is everything that's covered in section 25.5. Okay. So we're going to be thinking about this sort of beige box that we have here. In the figure shown here, we have some element in a circuit, right? This could be anything. This could be a battery. This could be a resistor. This could be basically anything, right? All that's important is that we have some potential difference between points A and B, our two terminals here. So we have some VA and some VB. So we have some VAB, right? And we have some current going through this circuit element. Okay. So as charge passes through this circuit element, the electric field is going to do some work on this charge. Okay. As charge Q passes through this element, there's going to be a change in the potential energy associated with this charge that's going to be equal to Q VAB. Okay. Each of these factors could be either positive or negative. Our Q could be a negative charge or a positive charge, and VAB could be negative or positive depending on whether we have a potential drop or a potential increase across this thing. So again, either it's a battery or a resistor or whatever. So we can have the potential going up or the potential going down across this thing, right? So there's going to be no change. So there is a change in the potential energy, but there's going to be no change in the kinetic energy, right? We can't have a change in the kinetic energy because our I is constant. So instead, what this potential energy changing represents is the energy the potential energy which we're either losing or gaining is being transferred from or to some other source of energy, or some other kind of energy, I should say, right? And so let's say, for example, we have a positive Q. Then for VAB less than 0, right, there's going to be a net transfer of energy out of the element. So there's going to be a net transfer of energy from the circuit element that we have placed in here out to the rest of the system. So this would be something like a battery, right? So for positive Q and negative VAB, this thing is going to be like a battery. Or if we have, again, positive Q but now positive VAB, there's going to be a net transfer of energy into the element. So we're going to have something like a resistor or something, and we're pumping energy into this resistor. And in the case of a resistor, this is just going to turn into heat, right? So a resistor is going to heat up. Maybe this is like a heating element or some sort of a thing that's going to heat up. So we want some resistance there. The resistor is going to take this electric energy that we're pouring into it, and it's going to turn that into heat. Okay. Primarily, we're going to be interested in the rate at which energy is extracted from or delivered to our circuit element, right? So we're going to be either delivering or extracting energy from this circuit element, and we're interested in the rate at which this is happening, right? So for some amount of charge, some tiny amount of charge dq, we know that dq is going to be equal to I dt, right? So we're going to have some tiny amount of charge which is going to be equal to our tiny current times a tiny amount of, or our current, I should say, our full current times some tiny amount of time. So this is going to be a measure of how much charge is going to pass through our element in a time dt. Okay. And for this tiny amount of charge that's going to be going through in a tiny time dt, we're going to have a change in potential energy which is going to be equal to VAB dq. Okay, and so we're just multiplying through by VAB, and we end up with the expression that we see here. If we divide this equation through by dt, so we're wanting to get rid of dt basically from the right hand side, we're going to end up with the expression that we see here. And so we're going to end up with VAB dq dt is going to be equal to VABI, and this is no surprise, right? The time rate of change of our Q is like I, right? And so this should be sort of no surprise to us. And this ends up being our expression for power. We call this the power, which is the time rate of energy transfer. And it kind of gives us this cleaned up version, which I have sort of copied from the textbook here. And so we have the power delivered to or extracted from our circuit element is going to be equal to the voltage across that circuit element times the current in that circuit element. Okay, and the power is going to come in at SI units of watts, right? So we're going to have power coming in with SI units of watts. Okay, so we want to keep this equation 25.17 in mind. We're going to keep moving on. And so now we're going to kind of think about what if the circuit element that we're talking about in this beige box here, what if it's known to be a resistor? So what if we have power input into a pure resistance? Okay. If the circuit element is a resistor, then we know that our potential difference, our VAB, is going to be equal to IR, right? Ohm's law again. And so we can replace the VAB that we saw in the equation up here in 25.17 with IR, and we end up with an I squared R. Or if we wanted to, we could replace our I with a V over R, and we would just end up with a VAB squared over R, right? But thinking about this in terms of a resistor, it's often more useful to think about it in terms of this I squared R. And so what do we sort of have here, right? So here we have our VAB, which is just going to be our potential at point A minus our potential at point B, is going to be greater than 0, right? Because we're talking about a resistor here. And so we're going to have this equation representing the transfer of energy into our circuit element, right? And so in this case, the resistor is going to take energy, and it's going to transform this energy into heat, right? So we're going to have energy being poured into the resistor. The resistor is heating up, and that heat is sort of bleeding off into the environment, and so that's what's happening to our energy. Okay. So that's sort of one example of one element that we could have in there. We now want to look at the power output of a source. Okay, so I put the diagram first here, and we're going to have a discussion about it afterward, but let's take a look at the diagram first. So we have a diagrammatic circuit here first, and then maybe I'll scroll down a bit. Can I get both? Yeah, we kind of have the sort of actual physical thing that we're kind of thinking about when we're looking at this diagram here. So we have the EMF source. It converts non-electrical energy into electrical energy, right? So we have some sort of, say this is a battery, we have some sort of chemical reaction going on that's forcing these charges upstream, that's forcing them from low potential at the negative terminal to high potential at the positive terminal. It's fighting against the natural electric field that would be set up inside this battery. It's converting this non-electrical energy to electrical energy at a rate of well, it's EMF times the current, right? And its internal resistance is dissipating this energy at a rate of I squared R, right? And this just comes from this expression here. We have a small internal resistance to our battery or whatever, and so power is being dissipated at that rate, right? So the battery is kind of heating up as a current is passing through it, and the difference between our EMF times I and our I squared R is the power output of our source. Okay, so this is our source up here, and then we can think of connecting our source with some resistance-less wires here to some sort of an external circuit. We have a current that's set up, and something is happening in that external circuit, right? So in this case, we're kind of thinking about this setup we have here. We have like a big battery, and we have a headlight. I guess this would be a car battery, and we have a headlight connected to it. We have a current set up. Current passes through the headlight, heats up the filament here, and so it starts to glow white hot. We get light coming out. And that's kind of sort of what we're looking for there, right? So thinking about that diagram that we just looked at, we know that point A is at a higher potential than point B, and so VAB is going to be greater than 0, and so the power is being delivered to the external circuit, right? And we know the power is going to be delivered to the external circuit at a rate of well, P equals VAB times I, and this just comes from our expression up here. And so let me scroll back down here. And so for this source, we know that our VAB is going to be equal to our EMF, minus our current times our internal resistance, right? This is the potential difference across the terminals of our battery, if we want to think about it as a battery like we have it drawn above. And this is what's going on inside the battery. We have the EMF source and the internal resistance, right? If we then multiply through by I, we're going to see that we end up with this expression here, and hitting this VAB with an I gives us our expression for power. And so we can see that the power here is going to be equal to these two terms here. We're going to have the EMF times I minus I squared times the internal resistance. So what do these two sort of terms mean to us? Okay, this first term, this EMF times our current, is the rate at which the work is done on the circulating charges by our source. Okay, so our source is doing some work on these circulating charges, and the rate at which it's doing this work is equal to our EMF times I. Okay, and this I squared R term is the rate at which the electrical energy is being dissipated by the internal resistance of our source, right? So our source is not an ideal perfect source. It has some internal resistance, and that internal resistance is kind of working against us here in a sense. It's robbing some of that power that the battery could be providing, but there's no way around that, and so we end up having some of it dissipated by the internal resistance of the battery. Okay, and the difference of these two things, the difference of the rate at which the work is being done on these circulating charges and the rate at which we're bleeding off the power produced by our source, this difference is the net electric power output of this source. It's the net electric power output of our battery. Okay, so that's kind of how we want to think about that. And now another quick topic. We want to take a look at the power input to a source. Okay, so this is kind of a little bit of a different situation. What we have here is sort of like what happens in your car when you turn on your car. You're kind of using some of the power stored in your battery to first turn over your engine, but then when your engine is going, your alternator is feeding power back into your battery. Okay, so this is kind of what we have excuse me, going on here. So we have our original source, but now we hook the original source up to another source, but this new source is going to be a larger EMF source. Okay, and so what do we end up happening, or what do we end up having happen? We end up pushing the current back the other way, right? So if we look at the way we had the current flowing in this diagram, we have current kind of coming around here in a counterclockwise direction. But now we replace this headlight with the alternator, and we're forcing current back in this direction. It's a larger EMF, so it actually overcomes what the battery was doing and forces the current back in this direction. Okay, so sort of what's happening within the battery, within our original source when this is happening. Well, so as we said, I is now going to flow in the opposite direction, and so for the upper source, we're going to end up having a VAB, a potential difference across the two terminals, which is going to be equal to our EMF, but now it's going to be plus the internal resistance times the current. Why is this? Because usually we have the EMF working against its internal resistance to put power out of the battery, or I guess you can think of it in those terms. But now we have this alternator on the outside, which is sort of overcoming both of those things, and so both of these are adding up in the same direction, although our current is pointing in the opposite direction, right? And so these no longer add destructively. We're no longer subtracting, but we're now sort of overcoming both of these with the power produced by our alternator, or at least the current being forced through our initial source by our alternator. Okay, and so again, if we go through this whole procedure of multiplying through by I, we end up with an expression here, the same as we did above, except that now we have this plus where we used to have a minus, and so now we have this work being done on the first source rather than by the first source. So the battery used to be doing the work on the charge, right, and bringing these charges from low potential to high potential, from its negative terminal low potential to its positive terminal high potential. It was doing work on these charges, but now we've kind of flipped the system around, and now the system is doing work on the battery. So we have our new source with a larger EMF is doing work on the battery, and what it's doing is it's transferring this electrical energy into non-electrical energy. It's sort of storing energy in the battery, presumably to be used later to restart your car or whatever. And so this is sort of the setup that we end up with in that kind of a situation. So the textbook goes into a few examples here. Some of them aren't bad, but I really only like this one here. You can definitely, and I do sort of encourage you to take a look at the other ones, but I'm only going to go over one of them here. Maybe we'll do another one of them on our Wednesday meetings. But for now, I'll take a look at 25.8, and this is the power input and output in a complete circuit. And so we're sort of going back to the circuit that we looked at in example 25.5. And so I'm not going to redraw it here. I'm going to use their drawing of it, but their drawing has a little bit of extra stuff in it that we're going to have to talk about. And so we have the circuit that we looked at in 25.5. We want to look at the energy dissipated so I guess, basically just the energy dissipated by the internal resistance of the battery, what's happening as we have our external resistor in the circuit, and so forth, right? So we're basically going to look at all the elements of the circuit and see what sort of power we have going across these things. Okay, so let's take a look at this. Now, I'm kind of confusing myself here because I'm looking at the old diagram, but they have additional stuff added in here. So maybe what I'll do is I'm gonna highlight some of these things. So originally we didn't know that this was 8 volts, and we didn't know that this was 2 amps. This is what we calculated in 25.5, right? So in 25.5 we calculated 8 volts and we calculated 2 amps, and we found those answers. But now we've also added in these terms here, right? So these are the new ideas from this section that are being added into the diagram, right? So initially we had none of the stuff circled in blue or the stuff circled in purple. Then in 25.5 we figured out the stuff circled in blue, and now to help us try and figure out what we need to look at here in this example, we've added in these purple circled expressions, right? So let's take a look at this. What we're trying to find here is we are going to want to try and find what the rate of energy conversion in the battery is first. So first of all, we're going to be looking at this term here. We want to find what the rate at which our battery is converting, say, chemical energy into electrical energy here. Okay, and so this is pretty simple. We have all the numbers that we need. I think I have a solution heading down here, right? So we know that this is going to be the power, the rate at which the energy is being converted from chemical energy to electrical energy. Okay, and so this is just going to be our 12 volts times our 2 amps, right? And so let's take a look at that here. We can see that our EMF is in fact 12 volts, and we know that our current going around the circle is 2 amps, and so we can substitute in those numbers, and we're going to end up with 24 watts. Okay, so again, this is the rate of energy at which energy is being converted in this source. Okay. In the second part here, we're going to want to see what this term is, our I squared R, and this I squared R is what represents the rate at which energy is dissipated by the internal resistance of our source. So we can think of this as a battery, and now we're looking at the the rate at which energy is dissipated by this internal resistance. Okay, so let's take a look at that. We have these values. Again, this is just going to be 2 amps. This is going to be squared now, and the internal resistance is 2 ohms. We can see that from here, right? This is our 2 ohm resistor that's stuck inside of our source. If we do that calculation, we're going to end up with 8 watts. Okay, and so that is the energy being dissipated inside of our source. Okay, so we can kind of, the question doesn't ask us to do this, but we can kind of look at this and we can say, well, what's the power output of the battery or the source sort of in total? Well, it's going to be the power provided by the EMF minus the power lost dissipated in the internal resistor, and so we're going to end up with 24 minus 8, which is going to be equal to 16 watts, which is provided by our source. Okay, and so next we want to look at the electric or actually maybe the question did ask us to do that, did it? Hold on. Energy dissipated by the battery, the rate of energy dissipation in the 4 ohm, and the battery's net power output. Okay, yeah, so it did. So this is the net power output of the battery. Okay, and now we want to look at the power dissipated in our external resistor here, right? So we're going to have some power dissipated in our external resistor, our 4 ohm resistor here, and we have the expression for that written down right here. So we can pretty much right away jump to writing down our solution. We can kind of write it in 2 ways. We can see that VA prime B prime times I, that's what we have here, VA prime B prime times I. This is the potential difference across A prime B prime times the current flowing through that resistor. That's going to be equal to 8 volts times 2 amps equal 16 watts, right? Or we could have looked at I squared R. And what is I squared R? Well, again, I squared R is just replacing our VAB using Ohm's law. V equals IR. We pick up an extra I and an R, and we can simply redo the calculation. Obviously, it's going to end up being the same thing. This is just going to be 2 amps squared times 4 ohms, and this is going to be equal to 16 watts again. Same as they must be. Okay? And so that's just a quick example of how we can look at the power either sort of converted in these sources or the power dissipated in these resistors. Okay? And as I said, this is going to conclude our look at section 25.5 and really our work in chapter 25, and I'll see you guys in the next one.